geometric means is that it's pretty much, it's really, really similar to the altitude stuff we learned yesterday, but it's actually a bit of a simpler way to do it. So it's kind of a shortcut. So yesterday I taught you more of the hard lengthy way. And today we're going to talk about the shortcuts. All right. So first we got to actually talk about what geometric mean is. Now, when I say the word geometric, I'm not talking about geometry. All right. I'm talking about geometric in terms of a geometric sequence. So remember in Math 1, you talked about arithmetic and geometric sequences. Geometric sequences, you are typically doing what from one number to the next? So you want to remember? What operation? Multiplication. Arithmetic is addition. So when we're talking geometric in this case, we're talking about multiplying to get the mean. Okay? Now, in this case, mean still means average, but the average that you're familiar with is an arithmetic mean. All right, meaning you're adding numbers to get, and then dividing them to get what we need. So an arithmetic mean of two numbers, we're adding the two numbers together and dividing by 2. That's what you're familiar with. All right, this type of mean is your average. All right, that should be what you're familiar with. Now, this results in a number that's halfway between 2 being average, but there are other types of means, and that's the geometric mean. All right, so arithmetic means addition, geometric means multiplication. All right, so what a geometric mean of two numbers is that if you have m and n, which are two positive numbers, so we don't want any negatives in here, their geometric mean is given by m times n, and then you take the square root. So just like how arithmetic means you add them, then divide, geometric, you'd multiply them, then take the square root. Okay. So we're going to first just do some plain old geometric means before we start throwing triangles into the mix. So let's look at letter A. So if I want to take the geometric mean, all I'm going to do is do 2 times 8 and then take the square root. So what's 2 times 8? 16. What's the square root of 16? 4. So our geometric mean is 4. What about the next one? So take a square root of 4 times 9. What's 4 times 9? 36. Square root of 36? 6. All right. What about 5 times 10 square root? So what's 5 times 10? 50. We take the square root. Now, there's no nice square root of 50, so we'll learn about simplifying radicals later, but we're just going to leave it as a square root of 50 for right now. All right, so try D on your own real quick. Yes, ma'am. Say it one more time. You could put the decimals, but for right now, since we want it to still be in radical form, we're just going to leave it as a square root of 50. Still a number. It's just that's like the exact versus the rounded. All right, so what are you doing for letter D? Someone raise their hand and tell me. Lucas.
You're doing the square root of 6 times 9.
Right, so you're doing the square root of 6 times 9, which, what'd you get?
54.
Right, so you get 6 times 9 is 54. Do the square root. You get square root of 54. Any questions on how to just do a simple geometric mean? So again, this is the formula for a geometric mean. If you have two numbers m and n, and they need to be positive. Why do they have to be positive? Why can I not have one negative number? Because you have a negative square root. Now, when we get to quadratics, we're going to learn that negative square roots create what we call complex numbers. But for right now, we're dealing with real numbers. So we're not going to even try with negative square roots right now. Okay? Now, because of geometric names get their name from geometry, because they arise in many contexts in geometry. So now we're kind of in triangle land a little bit. So let's try exercise 2. So what is the side length of a square that has the same area as a rectangle with a width of 9 feet and a length of 16 feet? All right. So if we have a rectangle, it has a width of 9 and a length of 16. They want to know that if we had a square, so all four sides are congruent, what would the length of one side be? So let's call that x. So first off, how would we find the area of the rectangle? We just do what? Length times width. So length times width, if we do that, so we're doing 9 times 16, what's that equal to? So I'll put that in your calculator if you have it in front of you. It's what? 144. Okay. So guys, I got fans all around me, so you gotta use your loud voices because I'm deaf apparently. All right. So 144, that's our area. Now, the square, they want the exact same area. All right. So they want this area to be equal to 144. Now, typically, if you're finding the area of a square, what are you doing? Technically, it's length times width, but we can simplify that down to what?
Is it side squared?
Right. You can simplify it down to the side squared. All right. Because remember, what's special about a square? All the sides are congruent. So technically, if the length and width are congruent, we're just squaring that number. All right. So if we know the area and we know that x squared is going to equal our area, how do I solve it? So how do I undo a square? Square root. So if I take a square root of both sides, x would be equal to what? 12. Well, guys, guess what we just did? We technically did a geometric mean. All right? We multiplied 9 and 16 together, and then we took the square root of it. So what we just did right here was the geometric mean. We just kind of did a roundabout way of that. All right, now that's quadrilaterals, and that was a very simple example. But remember, in this class, it's all about the triangles. So let's talk about some of the triangles. So this is kind of a review of side splitter theorem, so 2.8a. So in the diagram below, points D and E lie on AB and AC, and DE is parallel to BC. which is distinguished by those arrows. If AD is equal to 5 and EC is equal to 20, and AE is equal to DB. All right, they want us to find the length of AE. So they said that AD is 5, EC is 20, and that AE and DB are equal to each other. So in other words, these two side segments are congruent. They want us to find the length of AE. Now, this is the perfect example of a side splitter. All right. So remember, side splitter is when you take the two sides of one triangle and set it equal to the two sides of the other side of the triangle. All right. But specifically the pieces of the sides. So basically your proportion is going to be the same side. All right. So our first proportion will be what? If we're just looking at this side, or two pieces of the side. 5 over x. All right. So that's our first piece of the side. So essentially your proportions is if you break the two sides apart separately. So this would be 5 over x is equal to, what is it on my other side? X over 20. So remember, side splitter, all you're doing is writing the proportion based off of your two sides. So one side is equal to one proportion. It doesn't really matter which way you put it, as long as you keep it consistent with the other side. So for example, if you put the lower side first for this proportion, you put the lower side first for the other one. Okay? It doesn't matter. So I can solve this by cross multiplying. So what's x times x? X squared, what's 5 times 20? 100. How do I solve that? Square root it. So x will be equal to what? 10. So AE is equal to 10. And if we look, those two sides are proportional. To get from 5 to 10, you multiply by 2. To get from 10 to 20, you multiply by 2. So it satisfies the side splitter theorem. Now, again, it makes sense in terms of the side splitter theorem because each piece of each side is proportional. In other words, 5 times 2 is equal to 10. That's the first side. And 10 times 2 is equal to 20. So in other words, we would multiply it by the same scale factor. Now, if we look here, what did we essentially do with that side splitter theorem with this particular one? Did we do a geometric mean technically here? Yeah. We technically multiplied two numbers together. And because this was x squared, when we multiplied that together, we had to take the square root. So this was technically also a geometric mean because we multiplied two numbers together, took the square root. So in terms of triangles, so the geometric mean of two numbers as a solution. The geometric mean of numbers m and n, the positive solution is this equation. So it's m over x is equal to x over n. So it's essentially the exact same proportion that we set up in part A of exercise 3. Now, why is that important? Well, it makes the altitude stuff a lot easier. All right. So the stuff that we learned yesterday, geometric means are kind of the shortcut. All right. Now, first things first, we're going to solve this problem. Well, there's not really a solving to it just yet, but we're going to write out this problem with our separated triangles like we did yesterday. All right. So the altitude is QT, and the hypotenuse is RS for the big triangle QRS. So I'm just going to redraw my big triangle just so we can see it clearly. So this is SQR. Q is the right angle. Let's say S is your 1 tick angle and R is your 2 tick angle. Now, the side lengths that they have is A, B, and C. All right, so there's no actual side lengths yet. They just using letters. All right, so those lowercase letters are side lengths. Now, what would my medium triangle be? So if I'm looking at my medium triangle, so this one right here, the right angle needs to be on top. So what big letter goes with the right angle? T. Now we know the 1 tick's got to be on the left and the 2 tick has got to be on the right. So which big letter does the 2 tick angle connect to on the medium triangle? R. It's already marked over here, so it stays consistent. So that leaves us with Q as our small angle. So the length of QT is H, the length of QR is B, and the length of TR is E. And then lastly, our small triangle. Right angle on top, 1 tick on the left, 2 ticks on the right. So my small triangle's right here. So what letter goes with the right angle? T. What letter goes with the 1 tick angle? S. Which leaves Q as the 2 tick. So if I label the sides, ST is D, TQ is H, and SQ is A. So this is just review from yesterday. Now, using the similarity of the two triangles from A, show that the length of the altitude, which is H, is a geometric mean of the lengths of the two partition segments of the hypotenuse RS. So those lengths are D and E. So what we're doing up here is the altitude is H. All right, so right here. And we want to know if it's a geometric mean of the lengths for the two partition segments, which is D and E. All right. So we're going to set this up like a similarity proportion. So we're looking at the medium triangle and the small triangle. So the orange and the green. What would be my first proportion with two corresponding sides? So similar to what you did this morning with the warm-up. Two corresponding sides. What's one proportion with two corresponding sides? Okay, you're just using the letters. So we're using the little letters. So what's one set of corresponding sides lengths? So QT and what is corresponding? So QT on the medium triangle, what's its corresponding? No. ST. All right. So H and D are two sets of corresponding sides. So H over D is our first proportion. What would the second proportion be with my other set of corresponding sides? So that would be E and H. E, E and H. So E over H. Now, we're just going to cross multiply this, okay? So if we cross multiplied, what's H times H? H squared. What's E times D? ED. We'll just write it as E times D. So guys, this is a literal equation. We're not actually solving for anything. Well, technically we're solving for H. So if we solve for H, how do I get the H by itself? Take the square root of both sides. So the squares cancel out and H is equal to the square root of E times D. Now my question to you is that not a geometric mean? Isn't that the formula for geometric mean? Yeah. So this is the exact formula for a geometric mean. So now we already drew the smaller right triangle as the same orientation as the big triangle. Okay, we already did that. So now we showed that between the medium and small, if we did it in terms of the altitude, we get a geometric mean. Now let's look at the small and the big. All right. So we're going to show that the length of QS is a geometric mean of the length of SR and the length of ST. So now we're looking at the length of QS on the big triangle, so A, and we want to show that it's the same geometric mean as the length of SR and the length of ST. So ST comes with the the smaller triangle. All right. And then we also have an SQ over here too. So we're using the stuff that's highlighted in green. So we're doing the same thing that we just did. We're going to make a proportion with the corresponding sides. So let's just start with our big triangle. I'm just going to pick a side. I'm just going to say SQ or A. So I'm talking about A on my big triangle. So I have A over, what's the corresponding side on the little triangle? D. So A over D would be equal to, so C is my other side on the big. So what's that corresponding side on the small? It would be what? So I'm looking at C on the big. So what's the corresponding on the small? A. So I cross multiply and I get A squared is equal to D times C. Now, if I solve for A, I'd still take the square root of both sides. So A would be equal to D times the square root of D times C. So is that not a geometric mean? Did we not come up with a formula for geometric mean? Yes. So we still got a geometric mean. Now, why did we do all that? It's to explain the next part, which is essentially how we find the shortcut for the altitude hypotenuse relationship. Okay, so this relationship will let us take what we need without having to separate out the triangles. Okay, so geometric means and right triangles. An altitude to the hypotenuse of a right triangle is the length that is a geometric mean of two segment lengths partitioned along the hypotenuse. This is the most common. Then the length of either leg and the geometric mean of the length of the hypotenuse with the leg partition segment is the hypotenuse adjacent to the leg. Now, that's a lot of words, but I have two different tricks for what this is called. I'll show you in a second. But the first one, so the stuff highlighted in yellow, this creates what we call the T trick, which is essentially what we did for letter B up top. So when I'm talking about C trick, think about the letter B from the previous. The green is what we're going to call the ear trick. And that's similar to what we did with letter D of the previous. Now, I'm noting this because I'm about to show you what those tricks are. All right. So if we look at this triangle, given the right triangle EFG, the altitude is f of h, and it's drawn to the hypotenuse EG, partitioning into two lengths, 4 and 16. We're going to determine the altitude FH. So we're going to call that A. This is the T trick. And what the T trick means is that if you look right here, do you see how that makes a T? All right. That's the altitude and then a big hypotenuse of the right angle. Okay, so the two partition sides. So the T trick is the formula side 1 over the altitude, and it's equal to the altitude over side 2. And it doesn't matter which one you pick for which. So I said my altitude is A. Ah, crap. All right, so I said that my altitude is A. Oh, I know. We're still working. All right. So my altitude is A. So that means that to set this up, I would have 4 over A. So I just picked one of the sides and put over A. And then my other would be A first over 16. Now, then the length of side EF in simple Radulus form. So let's call that L. All right. So EF we're going to call L. Now, here is the ears. All right. So this is the hypotenuse, which we add together will give us 20. What the ears is that if you take the side length that formula would be side 1. All right, we'll pick this up tomorrow. No homework tonight. We'll pick up tomorrow. There is a Delta Math for 2A that you guys should be working on, though.
Does it matter what side I do first?
Nope. You'll get the same thing either way.